Cat and feline share 0 letters. 0, not a single one. Yet an AI instantly knows they mean almost the same thing. How? No dictionary. No thesaurus. No handwritten rules. To an AI, these words are just points floating in a massive 1,536-dimensional space. That magical understanding? It comes down to one single mathematical operation, the dot product. It measures how similar two vectors are, and it's the reason embeddings work at all. Let's see it. Here are two axes, a tiny 2D stand-in for that huge space. The word cat becomes a vector, this cyan arrow pointing out into the space. The word feline becomes another vector, the lime arrow. Watch how closely they point the same way. The angle between them is tiny. And the dot product? 0.89. Almost one, almost identical. The closer the angle, the higher the dot product. Closer means more similar in meaning. Quick gut check. What about cat and carburetor closer to 0.9 or closer to 0? In the next 14 minutes, here's what you'll understand. First, what a vector really is. Not an arrow, but a list of numbers. Second, the dot product formula. I'll show it once, then we focus on the intuition. And third, why embeddings work. Why words with similar meanings land near each other in space. So what is a vector, really? Not an arrow, that's just the picture. It's a list of numbers. For cat, something like 0.2, 0.8, negative 0.3, running on for 1,536 numbers. Where do those numbers come from? Nobody programs them by hand, and you can't look them up in a dictionary. The model discovers them during training. And each number is really a score for a hidden concept it invents. One dimension might track something like fluffiness, another machinery, another action. It carves the meaning of language into 1,536 of these features, all on its own. Seen cat millions of times in context, it nudges the vector so similar words land close by. That learned vector has a name, an embedding. The key property, distance encodes meaning. Close means similar, far means different. The space has 1,536 dimensions. We just squash it to 2D to picture it. The math is identical. Here's the dot product formula, shown once. Multiply each matching pair of coordinates, then add them all up. In plain English, how much do these two vectors point the same way? Quick example in 3D. 1, 2, 3 dotted with 2, 0, 1 is 2 plus 0 plus 3. That's 5. One thing to notice, real word vectors don't use whole numbers like these. Their coordinates are tiny decimals and the vectors are scaled to the same length, so a perfect match scores close to 1.0, not 5. My example just uses clean integers to keep the arithmetic simple. That's the entire formula. Now forget the math, and here's a question to sit with. If two vectors point the exact same way, is the dot product high or low? What if they're perpendicular? The dot product measures how much two vectors point the same way. Parallel vectors pointing the same way score close to 1, maximum similarity. One quick note for the math fans, as long as every word vector is normalized to the same length, the dot product depends only on the angle between them. That's exactly what's called cosine similarity. Orthogonal vectors, at right angles, completely unrelated, score 0, and vectors pointing in opposite directions score negative. So back to our words, the dot product of cat and feline is 0.89. These are nearly synonyms, but cat versus carburetor, a car part, around 0.12, basically unrelated. This arrangement is called a semantic space. The model places words so that similar ones sit close together. Cat, feline, and kitten all end up in the same little neighborhood. They're semantic neighbors. Small distance between them means a high dot product, but carburetor sits far away, a large distance, and a low dot product. Here's something genuinely wild. You can do arithmetic with meaning itself. Take the vector for king, subtract man, and add woman. Where do you land? Almost exactly on queen. It's not a coincidence. Minus man plus woman is a direction in the space, a kind of gender axis the model learned on its own. Walk that direction from any word and you move to its counterpart. and it generalizes. Paris minus France plus Japan lands on Tokyo. A different learned a direction, the capital city of direction. So meaning isn't only where a word sits, it's also the directions between words. And the dot product reads both. Quick but important, a model never sees raw letters or even whole words. First, your text is broken into tokens, and tokens are often subword pieces. Unbelievable might split into believe. Well, cats becomes cat plus. That's how models handle words they've never seen before. Each token maps to an integer ID, a row number, and a fixed vocabulary the model was built with. And that ID is exactly what gets looked up in the embedding table. ID in, vector out, which is the pipeline we'll trace right now. Let's trace a single word do the pipeline. Step 1. You type the word cat, already a single token. Step 2. The model looks that token's ID up in a giant embedding table. Think of it as a dictionary and pulls out its vector, all 1,536 numbers. Step 3, now cat is a vector, ready for the neural network to process. That embedding was learned during training, so cat sits close to feline and kitten. Every word in the vocabulary gets its own vector, all arranged for usefulness. And once training finishes, this whole table is frozen, the dictionary is locked. The model never has to figure out where cat goes again. At runtime, it just looks up those 1,530 fixed-use coordinates instantly. Here it is for real, semantic search. You search for the word feline. We turn your query into an embedding, then take the dot product against every document in the database. Document 1, the tabby cat jumped over the fence 0.91. Hi. Document 2, dogs are loyal companions 0.24. Both animals, but not that close. Document 3, the lion is a feline predator 0.89. Nearly identical to the query. Document 4, cars need motor oil 0.11. Completely unrelated. Document 5, the kitten played with yarn 0.87. You never typed lion or kitten, yet the engine found them. That's semantic search, powered entirely by dot products. And think, a plain keyword search for feline matches none of these. How many would it miss? One more refinement, and it's a big one. The word bank has just a single row in that frozen table, but it clearly carries two completely different meanings. We fished from the river bank. Here, bank belongs near water, shore, and nature. I deposited cash at the bank. The very same word now belongs near money, finance, and accounts. So modern models don't stop at the lookup. The frozen table gives a starting vector, and then the model adjusts it based on the surrounding words, same token, different context, a different final vector. How does a model fold in the context like that? That's called attention, and it's a whole video later in this series. Why does this matter? Embeddings power search everywhere. Google, Bing, every recommendation system, every LLM. Vectors are the language of neural networks. Everything inside a transformer is a vector. Embeddings are just the front door, and the dot product is the fundamental operation, measuring similarity, computing attention, and as you'll see, every matrix multiplication is built from it. You now get it. Distance in vector space IS meaning. Closer words, similar meanings. That's the whole idea. You just learned vectors and dot products, the foundation of embeddings, search, and neural networks. Next up, matrices and matrix multiplication. Why a 70 billion parameter model takes 10 times longer than a 7 billion one. This is video 1 of 7, and each one builds on the last, so watch in order. Video 2 is all matrix multiplication. Follow the series, and I'll see you there.